Hello, good morning. Welcome to the scheduled session of the course Power Plant System Engineering. So this is week 8, and in this week we will have a look into the different kind of condenser and we will solve problem for that. So let me go to the slides. First I'll share my screen. Yeah, so I have shared my screen. The meeting would be open and anybody can join in between. So let me start the session and go to the slide. Okay. Yeah. So welcome again to the eighth session of the course Power Plant System Engineering. And the session is rescheduled. Okay. Then I'll move to the topics covered in the past week. Okay. So the topics we have covered are the condensate feed water system, then direct contact condensers, surface condensers, regenerative cycle, then closed feed water heaters, open feed water heaters, boiler treatment concepts, then the circulating water system, in which the system classifications, cooling lakes, cooling ponds, dry cooling tower, we have learned. Sorry. Then the wet cooling towers, in which we have learned about the mechanical and natural draft types. Okay. Then psychometric terminology we have learned about. Then the psychometric calculations. Then we have solved assignment number 8. The same assignment we'll solve here. Okay. The aim of the session would be the same to solve some problems and we'll give a quick summary of the topics covered. However, this session we won't have much time. Okay, because the topics covered in this week are vast, so I will solve the assignment problems and one classroom problem. However, I just look up at the summary. So, in the first lecture, we have learned about the condensate feed water system, direct contact condensers, and surface condensers. Then we have looked the condenser the state of steams in the condensers on the TS diagram. Then the different types of direct contact condensers are the spray condenser, then barometric condenser, then jet type condensers. So these three types of condensers comes in the category of direct contact type, that is spray, barometric, and jet condensers. Then the surface condensers, which are essentially to be the cell and tube type heat exchangers. Okay, and a cell and tube type heat exchangers can have multiple tubes. Okay, and in the condenser design, we calculate the length of the tube, number of tubes, and if the length is given, then we have to determine the diameter based on the logarithmic mean temperature difference and what uh, logarithmic temperature difference and the overall heat transferred and the overall heat transfer coefficient U. On the basis of that, we can design a heat exchangers, which is essentially to be we are talking about the condenser here. Okay, then we have learned about de-aeration. So de-aeration is nothing but the removal of non-condensable gases that can harm the system, and the non-condensable gases can harm the system in the following ways. First one is the total pressure of the system, that is condensing pressure, can be increased because each constituents has its own partial pressure. So if the condensable if the non-condensable gases would be in the system, then the condensing pressure can get increased. Then second effect is they blanket the heat transfer surfaces, resulting in the severe decrease in the condensing heat transfer coefficient. So they can also decrease the overall heat transfer. Then they result into the chemical activity. Okay, mainly corrosion and formation of hydrides. So these are the things. Then we have learned about the heat transfer analysis, the terminal temperature difference. Okay, the terminal temperature, sorry, the terminal temperature difference is defined at the temperature difference at the outlet. Let me draw here. So if this is the heat exchanger, this is the condensing steam, this is the horizontal line. So this is the horizontal line. This vertical axis is showing the temperature, and this is showing the length of the heat exchanger. This is the hot stream, or we can say the steam is condensing, which is denoted by this horizontal line. This is at the high temperature TH. Temperature would be constant during the condensation. Then this is the cooling water. Okay, so this is going like this is going like this, which is essentially a counterflow heat exchanger. This is the temperature of inlet steam, TCI, TCI, and it's TCE, the cold temperature at the inlet and the cold temperature at the exit, TCE. Okay, so this temperature difference is called the terminal temperature difference, which is essentially to be TH minus cold temperature at the exit, cold fluid temperature at the exit, which is essentially the cooling water in the case of a heat exchanger. Okay, then other heat transfer analysis we did a different formulation to design the heat exchanger. So these formulas I will discuss when I will solve a problem based on the design of the condenser. Okay, different design calculations and all. In the lecture 7, we have learned about the regenerative cycle, closed feed water heaters, open feed water heaters, and boiler treatment concepts. Okay, so this closed and open feed water heater. For that, we have learned about the TS diagram in the past lectures. So no need to repeat the things here. Okay, and then we have solved some problems here also. Then in third lecture, the circulating and wet cooling. The circulating water systems in which system classifications, cooling lakes, cooling ponds, dry cooling tower, and wet cooling towers we have learned about. So this is basically the theory, and some formulas are also there, and these things we will look into the while solve the problem. Okay, and then we solve, I think, one problem on the psychometry. So these things are there. So this is the quick summary of the things we have done. Now let me move to the problems to solve. So here we go. So, so here is the first assignment problem. Okay, so let's start with this. Okay, it is saying the primary aim of the condenser is to condensate the exhaust steam from the turbine to recover the high quality feed water for reuse in the cycle. Okay. So if the condensing pressure, we look on the TS diagram. So if this is TS diagram, and this is the DOM. Let me draw the process to another pen. So this is what we have learned earlier is the Rankine cycle. Okay. This is process one, state one, two, three, and four. This is at higher pressure P1, the boiler pressure. This is condenser pressure P2. So here the heat is supplied Q in the boiler, and here heat is rejected in the condenser. The condensing process is zero point 0.2 to zero point 0.3. Okay, and what we done here, like the mentioned in the statement, condense the exhaust steam from the turbine. It condenses the exhaust steam from the turbine. So this point 2 is the turbine exit. So the steam is coming from this and it is condensing in the condenser. Okay, so the till here the statement is true. To recover the high quality feed water for reuse in the cycle. Okay, so from here this heat is supplied to the feed water. This QR is supplied to the feed water. Supply to feed water. Okay, this heat rejected from the condenser is supplied to the feed water for reuse in the cycle. So the whole statement is true. This is the same operation which is done in the condenser. Okay. So next statement is in the surface condensers. The condensate and the cooling water mix directly to the heat exchangers. So in the surface condenser, the condensate and the cooling water does not mix with each other. They act as the different streams. So this statement is false. However, this statement is true for the direct contact type condensers. So instead of surface condenser, instead of surface condenser, instead of surface condensers, in the direct contact type condensers, in the direct contact type condensers, the condensate and cooling water, cooling water mix directly to exchange the heat. Okay, so this statement is true for the direct contact type heat condensers, not for the surface condensers. Moving to our next problem, the process of removing the non-condensable gases in the surface condensers is called the deaeration. So this thing we have learned in the deaeration, we remove the non-condensable gases from the condenser. So this statement is true. Also, we have learned about the adverse effect if we don't remove these non-condensable gases from the condenser. So let me write it here. The adverse effect of non-condensable gases, adverse effects of non-condensable gases on the condenser. So first one is it they increases the condenser pressure. They increases the condenser pressure, which is not desired because for the maximum power generation, we need to keep the condenser as low as possible pressure for the maximum power generation. So these non-condensable gases try to increase the condenser pressure. And second one is they decreases the heat transfer rate by the blanket action. they decreases the heat transfer rate. They decreases the heat transfer rate. Then third one is they cause the chemical activities like corrosion and pyrites formation, like the corrosion and the hydride formation. Okay, so these three are the adverse effect of the uh, non-removal of the non-condensable gases. So to avoid these three things, we have to remove the non-condensable gases from the condenser, and the process is called the deaeration. Okay. Next is a fluid in closed type uh, feed water in a closed type feed water system. Water encounters the heat transfer zone of. Okay, so let's draw it in the PS diagram for the closed feed water heater system. Okay, so in this uh, system, the water, suppose this is the condenser pressure. So water moved from here to here and then also came here. Okay, so these three states. Okay, so de-superheating, condensing, and the subcooling. So in the closed feed water heater system, okay, the water encounters. Okay, so the some stream will go like this, and yeah. So in the closed feed water closed feed water heater system, the water encounters the heat transfer zone on the desuperheating, condensing, and subcooling, all of them. So here option D would be the correct option. Okay. So in the fifth problem, the statement is the circulating water systems are classified once through closed loop and combination systems. Okay, so this statement is true. Okay, in actual, the circulating water systems are classified as once through closed loop and the combination system, as we have seen in the theory part of the lecture. Okay, then sixth problem. The degree of saturation is the ratio of saturated specific humidity to the actual specific humidity. The statement is true or false. So this statement is false. This statement is false. False. Actually, the degree of saturation is the other way around. Let me write the definition of it. So the saturation ratio is uh, degree of saturation. The degree of saturation, or it is also called the saturation ratio. The degree of saturation or saturation ratio. It's defined as the ratio of is defined as the is defined as the ratio of specific humidity of specific humidity of actual air to the specific humidity of saturated air at the same temperature. At the same temperature. So the provided statement is wrong if the statement would be other way around, like the degree of saturation or the saturation ratio is defined as the ratio of specific humidity of actual air to the specific humidity of the saturated air at the same temperature. Okay, so the definition in the provided statement is twisted, so this statement is false. Next is the numerical problem. Okay, so they have asked the problem statement is for a fluidized bed. The okay, so actually this problem is from the next week, I think. We will anyway we will solve it here. So for a fluidized bed, the bed particles are fluidized by air under ambient conditions, and the density of a loosely packed bed is rho b kg per meter cube, and the density of of the solid is 3000 kg per meter cube. The void fraction is given as 0.5, and we have to find the density of the loosely packed bed rho b in kg per meter cube. So this is the fluidized bed combustion. Okay, the density. Let me write the things provided here. The density of the density of loosely packed bed provided as rho b. Then the density of solid particles, the density of solid particles rho s is equals to 3000 kg per meter cube. The density of rho b is also kg per meter cube. Then the void fraction, fraction alpha is equals to 0.5, then we have to find out the density of loosely packed bed. Rho v is equals to what? Then we know that the void fraction can be defined as void fraction can be defined as alpha is equals to 1 minus the density of the loosely packed bed to the density of the solid particles. Yes, density of the solid particles. Question number one. So putting the values, putting the values, alpha here is 0.5, which equals to 1 minus rho b we have to find out, and the value of rho s is 3000. So rho b by 3000 is equals to 1 minus 0.5. So density of loosely packed bread rho b is equals to 0.5 into 3000. So rho b will come out to be 1500 kg per meter cube. Okay, so the answer would be 1500 kg per meter cube. Okay, so this would be the answer. Let's move to the next problem. It is saying that the ultimate analysis of unknown grade coal shows a higher heating value HBV of 35 megajoule per kg. We have to find out the lower heating value LHP if the latent heat of vaporization of water is 2.3 megajoule per kg. Okay, so this problem is simple. Uh, Here the higher heating value higher heating value HHV is given as 35 megajoule per kg. The lower heating value the lower heating value LHP we have to find out the latent heat of vaporization of water, latent heat of vaporization HFG is provided as 2.3 megajoule per kg. So we know that the difference of higher heating value and lower heating value is the latent heat of vaporization. While putting the values in this equation, the HHV is 35 minus lower heating value we have to find out, and the HFG is 2.3. So the lower heating value will be 35 minus 2.3. This would give heating value is equals to 32.7 megajoule per kg. This is an easy problem. Just we have to remember that the difference of higher heating value and a lower heating value is the latent heat of vaporization of the water. Then moving down to the next problem. So it is given that the steam condenses at 44 degrees centigrade in a surface condenser by releasing heat to the circulating water. So the steam is releasing the heat to the circulating water, or sometimes we say it is cooling water. Then water enters at to the condenser at 30 degrees centigrade and leaves at 40 degree centigrade. From the given statement, solve the problem 9 and 10. Okay. So in problem 9, the terminal temperature difference TTD they have asked. Okay. So let me draw the system. So this y-axis is temperature and axis is length of the heat exchanger. So I steam is condensing at 44 degrees centigrade. This is my TH, and water is entering from here where this will have some curve. Okay. The water is entering here, PCI, and this will be the PC exit. So here pH is equals to 44 degrees centigrade. TCI is equals to the TCI is the inlet temperature of water, or cold steam, which is water here. This is 30 degrees centigrade. It is entering at 30 and exiting TCE is 40 degrees centigrade. Okay. So we know that the TTD is the temperature difference of the hot and cold streams at the exit. So TTD would be the TH minus TCE. Basically, this temperature difference would be the TTD. Okay, so while we put the values here, that is 44 minus 40. So from here, TTD would be 4 degrees centigrade. Okay, the terminal temperature, the value of the terminal temperature difference would be 4 degrees centigrade. This would be the answer, would be 4 degrees centigrade. Then moving to the next problem, here we have to determine the logarithmic mean temperature difference. So let me first define the logarithmic temperature difference. This is the temperature difference which take care of the temperature difference of hot and cold steams along the length. Okay, we know that along the length, the temperature of hot and cold steam would be decreased. Okay, and so this is the temperature difference which is the logarithmic mean temperature difference, which take care uh, the variation of temperature difference along the length and give us the uh, single value. Okay, single value of temperature difference between the cold and hot fluid streams. Here we have to determine the same thing, the temperature, the logarithmic mean temperature difference. For that, let me draw first the temperature profiles. Okay, although we have done it in the last problem, no issue. Here again. Okay, so these are the axes, temperature and length. This is my hot fluid streams, which is steam condensing at 44 degrees centigrade, and this is the entry temperature of the entry and exit at the of the cooling tower or cooling water. Okay, so this could be a parallel or counter flow heat exchanger. Anyway, the LMTD would be the same for in both the cases. So this is TH, the high temperature, the temperature of the hot steam. This is TH. This is TCI, and this is TCE. In the calculation of the logarithmic mean temperature difference, we have to determine the temperature difference at the inlet and the temperature difference at the outlet. This temperature difference is called delta Ti, and this temperature difference is called the delta Te. Okay, so now let me write the values here. Okay, so here pH is 44 degrees centigrade, TCI is 30 degrees centigrade, and TCE is 40 degrees centigrade. So the temperature difference at inlet delta Ti would be pH minus TCI, that would be 44 minus 30, it would be 14 degree centigrade. Similarly, the temperature difference at the exit delta TE would be the TH minus TCE, that would be 44 minus 40, that is 4 degrees centigrade. And now the expression for the LMTD, the logarithmic mean temperature difference, the logarithmic mean temperature difference LMTD can be defined as LMTD, sorry. The LMTD can be defined as delta Ti minus delta T divided by ln of delta Ti divided by delta Te. So putting the values in one, let me take one slide. Okay. So the when we put the values here in equation number one, then LMTD would be the delta TI value is 14 minus delta TE value is 4 divided by 1 of delta TI which is 14 and delta TE which is 4. When we solve this, then the LMTD will come as 7.98 degrees centigrade. Okay, so the value is coming as 7.98 degrees centigrade. One thing to notice is that the temperature difference at inlet is 14 degrees centigrade and at the exit is 4 degrees centigrade. So we have to notice is that the LMTD value would always be the in between the temperature difference of inlet and outlet. So the 7.98 is in between of the 14 and 4. So this is the way to cross check whether our calculation are correct or not. So this LMTD value would always in between of the temperature difference at the inlet and exit. Okay. So these 10 problems are the previous year assignment. Now I will solve this one classroom problem. Okay. So this problem is will cover all the concepts of the condenser design. Here we will determine the required mass flow rate, the rate of air leakage into the condenser, and the number of tubes and length of the tubes. Okay, so and this is related to this is the complete design of a condenser. So we will solve it. Okay. Okay, so the problem statement is likewise. So the problem statement is a surface condenser receives 250 tons per hour of the steam at 40 degrees centigrade with the 88% of quality. Fine. The cooling water enters at 32 degrees centigrade and leaves at 38 degrees centigrade. Fine. The pressure inside the condenser is 0.078 bar and the velocity of circulating water is 1.6 meter per second. The tubes of condenser are having have the 25 mm outer diameter with the thickness of the 1.25 mm. So with the help of this provided thickness, we can determine the inside diameter of the condenser tube. Then we have to determine the rate of flow of the cooling water, the rate of air leakage into the system, the length and number of the tubes, and the whole overall heat transfer coefficient is given as 2560 watt per meter square Kelvin. So first, we will make the temperature profiles. Okay, we will do the problem. Okay, so the temperature profiles would be like this. The steam is condensing at, okay, let me take the another color pen. This would be the hot fluid stream, and this would be the cold fluid stream. Parallel or counter doesn't matter when while any of the fluid is undergoing the phase change. Okay, so the steam is condensing at temperature TH. Okay, the this is the inlet temperature of cooling water. I will denote it CWI, and this is the exit temperature of the cooling water. I will denote it cooling water exit CWE. Okay, and these axes are obviously denoting the temperature and length of the tube of the heat exchanger. Okay, so this is the first thing. Let me write these values first. So here uh, TH is given as 40 degrees centigrade, which is here, the same is condensing at 40 degrees centigrade. The inlet temperature of the cooling water CWI is 32 degrees centigrade, which is provided here, 32 degrees centigrade, and the exit temperature of the cooling water CW is provided as 38 degrees centigrade. So these are the temperatures provided. Let me make the schematic of the condenser. So let me make it here. Okay, let me make it here only. So this is the condenser, this is inlet, the steam, and this is exit of the steam. We would write it like this. And these are the tubes I will make. These are the condenser tubes. Okay. So these are the condenser tubes. Let me put the symbols here. So from here, the steam is entering. Okay. At the temperature TH, mass flow rate m dot s, and at the having the quality of x. From here, the cooling water is entering, and from here, the cooling water is exiting. Okay. So this is mass flow rate of cooling water, MCW. This would be the same MCW, and which is having the inlet temperature of TCWI, and Take another color pen. T, net temperature T, CWI, and exit temperature T, CW exit. Okay, so these are the things they have provided to us. And yeah, let me write the complete data. Here, TH, I have written the mass flow rate of the steam m dot s is provided 240 tons per hour, tons per hour, which would essentially be equals to 240 into 1000 divided by 3600 kg per second, kg per second. So the m dot s, when we solve it, then it would come 66.67 kg per second. Okay, so this is the things, and the provided quality of the steam is x is equals to 0.88. So these are the things provided, this set of things. Then the next things provided. Okay, so these things are only required for the first part of the problem, so we won't write the much things. Okay, we'll solve the first problem only. To calculate the rate of flow of cooling water. One thing remained. Let me draw the pressure on the TS diagram. From there, we will get to know what we exactly have to do. This is T, this is S, this is the paper down. Okay, so let's suppose this is the condensing line. At here the temperature is given 40 degrees centigrade at the 40 degrees centigrade. Okay, from here the steam is entering at here. Another color pen. This is the steam is entering at point. This is like this is my cycle. 1, 2, 3, and 4. 1, 2, 3, and 4. Okay. So here at this from 2 to 3, the heat is reacting to the cooling water. I will write is Q dot CW, and here at 40 degrees centigrade, the enthalpy would be HF, and here it would be Hg, and here at point 2 x is 0.88. Okay, so first what we have to do, we have to determine, we have to find out the value of HF and Hg at the saturation at 40 degree saturated temperature from the steam table. So we will write the values here. First let me give the overview. The this QCW would be the m dot steam into H2 minus H3. Okay, so we will calculate this Q dot CW, and based on that we will be able to determine the mass flow rate of the cooling water. So Let me move to the another slide. So at 40 degrees centigrade, at 40 degrees centigrade, from the steam table, from the table, HF is, I determined these values from the steam table. HF is comes out to be 167.53 kilojoule per kg, and Hg is 2753.5 kilojoule per kg. Okay, this is 2573. 2573. Okay, based on that, we can determine the enthalpy at point 2, and the enthalpy of point 3 would be HF only. So the enthalpy of point 2 H2 would be HF plus X into Hg minus HF. Okay, so while you put the values here, then H2 would be 167.53 plus the quality is 0.88 into Hg is 2573.5 minus 167.53. This value will comes out to be H2 is equals to 2284.78 kilojoule per kg, and S3 value we have already. S3 is equals to HF is equals to 167.53 kilojoule per kg. Now our first aim would be the heat transfer to the cooling water, Q dot CW. The heat transfer to the cooling water transferred to the cooling water, Q dot CW is equals to mass flow rate of the steam into H2 minus H3. Okay, so we are having all these values. So while we put the values, then QCW m dot s we have just calculated, determined 66.67. Okay, so this 66.67 into H2 value is 2284.78 minus 167.53. So when we solve it, then this heat transfer rate to the cooling water will come out to be 1411.57. This value will come out to be approximately 14 14 11 57 141157 kilowatts. Okay, so like this we have determined the heat rejected in the heat condenser, or also we would say the heat received by the cooling water. Next, we are having the inlet cooling water temperature is 32 degrees centigrade. The exit cooling water temperature is 38 degrees centigrade. Let's consider the specific heat of the cooling water is 4.187 kilojoule per kg Kelvin. Then the heat received by the cooling water would be Q dot Cw is equals to mass flow rate of the cooling water into specific heat of the cooling water into the exit temperature minus inlet temperature. Okay, so while we put the values here, the value we got is value of the heat transfer rate is 11. No, it is 141157 is equals to the cooling water. This is 4.187 into this value is 38 minus 32. So from here, the mass flow rate of the cooling water will come out to be is 5618.87 5618.87 kg per second. So this is the answer for the part A. Okay, this would be the answer for part A. In part A, we had to determine the mass flow rate of the cooling water. Yeah, so from here, part A was started, and this is the answer for part A. The mass flow rate of the cooling water would be 5618.87 kg per second. Now moving to the part B. So in part B, what we have to determine, we have to determine the rate of air leakage into the condenser. In part B, rate of air leakage into the condenser. What would be the rate of air leakage into the condenser? We have to determine. So for that, let's first we have to determine the total condenser volume flow rate. Okay, so the total volume flow rate would be total volume flow rate V dot would be the mass flow rate of the steam into the specific volume at point 2. This would be my equation number 1. Let's suppose. So At 40 degrees centigrade, my volume of fluid, the specific volume of fluid was 0.001 meter cube per kg, and volume of the gas, specific volume of the gas was 19.515. This is 19. Write it again. 19.515 meter cube per kg, and the quality we are having 0.88. So by the help of this, we can determine the specific volume at point 2. V2 is equals to Vf plus X into Vg minus Vf. Okay. While we put the values in this, then V2 would be 0.001 plus 0.88 into 19.515 minus 0.001. So while we solve this, the value of V2 will come out to be, value of V2 will come out to be 17.173 meter cube per kg. Okay, will come out to be 17.173 meter cube per kg, and m dot s we are already having 66.67. So from equation 1, so from equation 1, my v dot would be m dot s into v2. M dot s we are having 66.67. V2 we have just calculated 17.173. So V dot will come out to be 1144.92. 92 meter cube per second. So this value we will use later. Let me club it. Okay. Then for air we can write, the ideal gas equation P air into V dot, because air will occupy the whole volume, and mass flow rate of air, write it from different color. Okay, so the P air into V dot is equals to m dot air into universal heat transfer coefficient for air into temperature. Equation number 2. So here we have to determine the P air basically. Okay, the condensate pressure is given here, like what was the condensate pressure given. Now it's the time to get the values from here. So the condensate pressure given as 0.078 bar. Okay, so pressure is given The condenser is 0.078 bar, and the saturated pressure saturation pressure at 40 degrees centigrade we have find out from the steam table. It is the 0.07385 bar, and we know that the condenser pressure would be saturated pressure plus air pressure. Okay, so the P air would be condenser pressure minus saturation pressure, which would be 0.078 minus 0.07385. So from here, the P air will come out to be 0.00415 bar, or when we convert into kilopascal, then P air would be 0.415 kilopascal. Okay, so this air pressure we have determined. Then next, what would be the from equation 2, we are having this P air, V dot, M dot air we have to determine, R air and T. So the R air value we are having, R air is 0.287 kilojoule per kg Kelvin. Then temperature is already given 40 degrees centigrade, which would be used in the Kelvin. So 40 plus 273, it would be 313 Kelvin. So now we are having all the values to use the equation number 2. Okay, so now from equation number 2, from equation 2, the P air into V dot is equals to M dot air into R air into T. Putting the values here, P air we have just determined 0.415, V dot we have also determined as 1144.92, point is not 1144.92 is equals to M dot air we have to determine, R air is 0.287 and T we are having 313 Kelvin. So while we solve it, we will get the air flow rate of 5.289 kg per second. 5.289 kg per second. So this is the air flow rate into the condenser. This would be the answer of our part number 2. Okay. So part A and B we have solved. Now in the part C we have to determine the length and number of the tubes while the overall heat transfer coefficient is provided. So part C, for the part C, we will need the overall heat transfer coefficient U is equals to U is equals to 2560 watt per meter square Kelvin. The outer tube area is given as 25 mm, which would be the 0.025 meter. The thickness of the tube is given as 1.25 mm. So the inner diameter of the tube would be the d naught minus 2t, which would be 25 minus 2 into 1.25, which would be 22.5 mm, which would be essentially 0.0225 meter. So these are the values provided in the question, and the values we have calculated are the heat transfer rate to the cooling water or the heat reacted into the condenser we have calculated as 141157 kilowatts. So this value we have just calculated. Now we know the heat balance equation would be Q dot cooling water would be the overall heat transfer coefficient into outer surface area into logarithmic mean temperature difference. So this will be the equation number 3. Now we have to find out the logarithmic mean temperature difference. Let me plot the temperature profiles here, although I have done it earlier, but to show here, we draw this TH, this is TH, this is T cooling water I, this is T water exit, this at inlet, this would be the temperature difference at inlet, T and delta Ti, and this would be the temperature difference at outlet, delta T E. So the values, this is 40 degrees centigrade, this is also 40 degrees centigrade, this is 32 degrees centigrade, and this is 38 degrees centigrade. If I'm right, then we can determine the value of temperature difference at inlet. Delta Ti is equals to Th minus Tcwi is equals to 40 minus 32 equals to 8 degrees centigrade. Then delta Te would be Th minus Tcwe, which would be 40 minus 38 is equals to 2 degree centigrade. Okay. Then the formula for LMTD, we know LMTD is delta Ti minus delta Te divided by ln of delta Ti divided by delta Te. Okay, so when we put the values here, it would be 8 minus 2 divided by ln of 8 divided by 2. So from here, my LMTD will come as 4.228 degrees centigrade. I will club these values and I will use this value in equation number 3 to get the outer surface area of the condenser. So now from equation 3, now from equation 3, we are having this Q dot CW is equals to UALMTD. So it would be the Q dot CW we are having 141157. It is in kilowatt, so I will multiply it by 10 to the power 3 to convert it into the watt. Then U value we are having 2560. Then this overall heat transfer area A naught we have to determine, and LMTD value we are having 4.228. So when we solve it, the value of the A naught we will get A naught is equals to 1304152 meter square. So like this, we got the value of the heat transfer area. Okay, now we know that this heat transfer area would be equals to the heat transfer area for the single tube pi d naught L into the total number of tubes n. Into the total number of tubes n. Let me consider this as equation number 4. Now here both the things I have to determine the length of the tube L and number of tubes n. So I need to use another formula here for the cooling water, like this is my cooling water circulating here. Okay, m dot cooling water, m dot cooling water. So the formula of this m dot cooling water would be the rho internal area EI, because it is circulating inside the tube, the AI into velocity of the water into the number of tubes. Okay, and this would be my equation number 5. So m dot cooling water would be rho. Let's consider rho of water is equals to 1000 kg per meter cube. This rho into this area, internal area would be pi by 4 into di square into V into N. This V value is given to us if we look at the problem statement, and it is given here. This V is the 1.6 meter per second. Okay, this V is the 1.6 meter per second. So we will put all these values here. The m dot cooling water we have just calculated 5618.87. We write the value 5618.86. kg per second. So I will write the values here. 5618.86. Raw value is 1000 into pi by 4. Di we have just determined at the earlier of this problem, and it is 0.0. Let's here. It is the Di value 0.0225. Okay, 0.05 square into velocity is 1.6 into n we have to determine. When we simplify this expression, then what we will get? The value of n we get the value of n we get 8832.5. So this can't be a fractional. So here the number of required tubes n would be 8833, and this would be the answer. So we will require 8833 tubes to transfer this much amount of heat and for this much of flow rate of the cooling water. This would be the answer. Now we will go to equation number 4. Now from equation number 4, now from equation 4, the equation 4 was A naught is equals to pi d naught L n. So we are having all the values. We will just put the values here. This is 13041.52. Let me check it is the correct value of a naught. Yes, 13041.52 will be equals to pi into d naught value we are having 0.025. L we have to determine, and N we have just calculated 8833. So when we simplify it, solve it, then we will get the value of length of the tube. L is equals to 18.78 meters. Okay, so this would be the complete answer for the part C. Okay, so here in part A, they have asked to determine the rate of cooling water, and that thing we have determined by the heat balance only. Then there are to determine the air leakage into the condenser, and we have determined it, okay, by the simple ideal gas equation. Then in the last problem, we have to design the heat exchanger. For that, we have determined the log between temperature difference. Then apply the heat balance equation, determine the heat transfer area. Then uh, by balancing the mass flow rate, the cooling water mass flow rate, we have determined the value of the number of tubes required, and by the calculated area, we have determined the length of the heat exchanger, length of the tube. So these are the problems I want to discuss. So Thank you.